Good morning. Um, we finished up chapter 10 on rotation, so we're moving on to chapter 11, and it's another chapter on rotation, so it's a follow-up. We did a really thorough look at chapter 10, and so we're prepared to move on. Now in chapter 10, we looked at rotational kinematics, right? Things, rotational displacements, velocities, accelerations, and then we looked at rotational forces, which were torques, and then we looked at rotational energy. And so the one thing that's left is rotational momentum, and that's kind of the focus of this chapter. We're going to be looking at a lot of the same things that we looked at last chapter, but kind of the focus is on angular momentum. So here it is, angular momentum. We use a symbol L, which I don't know if that was a good idea, but it seems like with linear momentum we used P, and that didn't make much sense either. So angular momentum is, we're going to find it can be expressed a couple different ways. So there's not just one specific formula that we always work from. We'll see that we've got to be a little flexible. But we could think of, let's see, linear momentum, P, was equal to mass times velocity. So if we do all the same thing in terms of rotational quantities, that would say that angular momentum, L, is equal to rotational mass, or rotational inertia, times the rotational or angular velocity. So the V becomes omega, the M becomes I, and the P becomes L. Now, just the same way that forces could be related to changes in linear momentum, torques can be related to any kind of a change in rotational or angular momentum. So that says if I've got a spinning object, the object tends to just keep spinning at the same rate unless there's a torque acting on it. Here's kind of the same thing there. Angular momentum turns out to be a conserved quantity. So it falls into the same category as, let's see, first of all, we introduced energy, and then we introduced the ideas of energy conservation. That if we isolate a system and kept track of what energy is coming in and out, we could do a little bookkeeping on energy, and we could actually solve problems using the idea of the principle of energy conservation. Then we had introduced conservation of linear momentum. That's turned out to be very useful. Well, now we're on to kind of our last, dynamics conserved quantity, and that is angular momentum. And so what it says is that if there are no external torques, if we don't have any torques going on, then the angular momentum variations with respect to time are equal to 0. So that means that I times omega would be a constant. So more formally, the total angular momentum of a rotating object remains constant if there are no torques acting on it, or if the net torque is equal to 0. So here's another slide that I kind of put together to outline the comparisons. Here is linear momentum, here is angular momentum. Now remember, they're vectors. So let's go back and think, well, vector momentum was equal to m times vector velocity. And what that looks like is px is equal to m times vx, py is equal to m times vy, pz. So I can look at all the components here and say, yeah, no big deal. Mass is the same whether we're looking at motion in the x or the y or the z. Angular momentum is more complicated, and that's because the rotational inertia is not a scalar. It's not just one quantity. It actually turns out that, let's think of this, if I have rotations around the x-axis, or rotations around the y, or rotations around the z, how do I decide how much angular momentum is there? And I actually have to go in and look at different axes and calculate different components of rotational inertia. Now, you guys don't have to do that. I'm only including this because in the last chapter we talked about the rotational inertia of an object depends on which axis we're looking, it's not like mass. Mass, it doesn't matter which direction we're looking at, X, Y, or Z. Mass is mass. But rotational inertia is not going to be the same thing if the object is rotating around a different axis. And so in general, we have to go in and calculate these. It's a 3x3 symmetric tensor. Now, in physics, quantities that are represented this way, that have not just one column of components, but they have, 3x3, they have 3 rows and 3 columns, they're referred to as tensors. Not a big deal, they just follow the rules for matrix multiplication. And again, you guys don't have to worry about it because we're not going to be doing any of these calculations. That's just in here so you guys have a more complete understanding of, how do I take into account all of these differences in the rotational inertia when we switch from one axis to another. Now here's what they were pointing out too, that Newton's laws of motion, the second law can be written down as, if I look at all the forces acting on something, that keeps track of how the momentum is changing. Well, the rotational analog is that if I look at all the torques, that will tell me how the angular momentum is varying. So if there's no torques, or 0 net torque, the object will just keep spinning with the same magnitude in the same, with the same angular momentum magnitude oriented in the same direction. Now, units are also kind of interesting here. Momentum then, if we look at the quantities here, momentum was in kilograms meters per second. We said that could also be written as Newton's time seconds. So we had these two different combinations of units. There's no particular unit assigned to momentum the way joules are assigned to represent energy. Angular momentum, on the other hand, though, when I put all the units together, it doesn't have the same units as momentum. So angular momentum is its own quantity. It's not interchangeable with linear momentum, although we'll see examples of switching back and forth in problems where we're keeping track of linear momentum and angular momentum. There's a relationship between them, but they're not the same quantity. So I can't take a certain 100 units of momentum and convert it to 100 units of angular momentum because they're not even the same units. Now with energy we could do that. If you remember in chapter 10, we looked and we said, here is what linear kinetic energy looks like, 1/2 mv squared. Here is what rotational kinetic energy looks like, 1/2 I omega squared. They could be interchanged in a problem. So if I have some rotational energy, that could be converted over into linear kinetic energy. But angular momentum and momentum, two distinct quantities. And again, it is kind of funny that we picked kind of these random letters to represent these. Now I do have to say, a friend of mine from high school and college, and even before that, went on to, he went into engineering and electrical engineering, and he worked for a company called I Omega. I Omega, this is ancient history I guess, I don't think I Omega is around anymore. They made external drives. So for memories, for computers, so you'd have computers with these drives that were spinning around. And it was a big deal. I Omega for a while was the kind of the top manufacturer of external drives. And it's just kind of interesting because I never knew, he worked for this company, I Omega, and I thought, I Omega, where does that come from? And then I realized this has got to be it. The things are spinning, right? The I Omega represents angular momentum. So I Omega comes from that formula. Anyway, it's too bad that the company, that name's not around. That would still be a good name, I Omega. All right, let's look at some examples of calculating angular momentum. Now there's two different ways we can think about angular momentum, and to kind of demonstrate that, here is Earth, here is the Sun, and here is Earth orbiting the Sun. It's orbiting at a distance of little r. And remember, that's center to center, right? Because this is, well, we're treating it as a spherical coordinate system. This is the origin of our coordinate system, and it's at the center. And all the formulas that we derive are based on looking at the center of that motion. So angular momentum can be written as, well, let's start up here. If we start with L is equal to I omega, I could be written as mr squared for that object. And then omega is omega, but wait a minute, V is equal to R times omega. If we make that substitution in for omega, it turns out angular momentum can be written as mv times r. So that's two formulas that allow us to calculate angular momentum. So I can either work in terms of the rotational inertia and multiply by whatever, the angular speed is, or I can work in terms of momentum. mv times r gives us the angular momentum. Now we'll see that more generally this is only true if the motion is circular. If it's elliptical, we have to, or if it's some other kind of a shape, we have to generalize that. Now, for the Earth's orbital motion, this is the mass of the Earth, 6 times 10 to the 24 kilograms. That's a lot of kilograms. And the radius of this circular motion that we're imagining is 150 times 10 to the 9th meters. And the period of the orbital motion is 1 year. And 1 year works out to be 31.6 million seconds, roughly, which is, the years fly by, because, by the time you've counted to 31 million, the year's over. Let's see. And then the velocity of the Earth in its orbital motion is given by, now, this is going to be given by the distance, 2 pi r, that's the circumference, divided by the period. So the speed of Earth in its orbit, that's 30,000 meters per second. All right? So you would think if we were moving at 30,000 meters per second, we would know it. But, what we've learned in physics so far in the course here is, hey, if you're moving at constant velocity, it's no different from just being at rest. The things... If you're working from one reference system that's moving with a constant velocity, things just feel like you're at rest. Okay, if you're moving right along with that system. That's what we're doing with planet Earth. Yeah, this works out to be something like 67,000 miles an hour, so that's a pretty good speed. So what we could do is this. We could say, do I want to use I omega, or do I want to use mvr? And I thought, I'll just use mvr. I know what the mass of the Earth is. We've just calculated what its speed is. And we looked up also information about the radius of the circular orbit. If I take the m, v, and r, what that worked out to be is 2.70, 10 to the 40th, kilograms times meters squared per second. Someone come up with a unit for angular momentum that we can use. Now, in addition to the orbital motion, Earth also has a rotational motion. So here's Earth, and let's say that, here it is rotating, and there is its omega. Now I know it's common, or it's kind of conventional, to say the Earth rotates on its axis, and that always sounded kind of funny to me. I thought, well, the Earth just rotates. What do you mean it rotates on its axis? It doesn't really have an axis. It just rotates. So here is the Earth rotating. Now it does rotate around its center of mass. So there is a center of mass of the Earth, and there is a rotational axis defined by, at any particular instant, what point is the Earth rotating around, and over, hundreds or thousands of years, or tens of thousands or millions of years, there are significant changes in Earth's axis of rotation. And so it's not like the axis is something you can walk up to and there it is, there's Earth axis right there. So Earth does rotate around its center of mass. So leave it at that. And so what we could do for this is we could go, well, this looks like chapter 10 kind of stuff. What we could do is say that the rotational inertia of Earth is 2/5 mr squared. So I plugged all those numbers in, I looked them up, they're here somewhere. Okay, maybe this is the first time this comes up. So 6380 million meters is the radius There's the mass again. And it says that the rotational inertia of Earth then is 9.77, 10 to the 37 kilograms times meters squared. Now, the rotation here is, let's think of this as omega. Omega is going to be equal to 2 pi divided by the period. And the period is it's about what we call 1 day. It's not our 24-hour solar day. It's a stellar day. It's a day, a rotation relative to the stars. And that works out, we've talked about this before, I think. That's about 4 minutes shorter. And so that's 86,164 seconds. So this is the omega value. So it's not spinning exceptionally fast in terms of radians per second. But I can take the I and the omega, put those numbers in, and that's how much angular momentum there is due to the rotation. Now you guys know, so we use the two formulas. So let's first point that out. We have now used the two alternate formulas here. We could use MVR, we said, or we could use I omega. And for the orbital motion, MVR seems convenient. And for the rotational motion, I omega seemed pretty convenient. Now when we look at this, the orbital angular momentum is much, much larger. It's larger by 6 or 7 orders of magnitude. Is there a way that we could combine these two angular momenta together? And you can. So what you could do is you do a vector addition. Now you guys know that the rotational axis of the Earth does not line up with the axis of its orbital motion. So if we go back to the orbital motion here, so here the direction of L would be coming out of the board because I've got, we'll see this maybe farther into this chapter. We kind of talked about it a bit in chapter 10 that the rotational velocity direction is perpendicular to the, or it's along the axis of rotation. Well, it turns out the angular momentum for a system like this is also along the axis of rotation. So we could add them together. So we could say, okay, there's a bunch of this orbital angular momentum, and here's some of the rotational angular momentum. That can be divided up into components. You could do vector addition. And planets can borrow back and forth the angular momentum. So for example, you guys may be familiar with the idea that the moon used to be much closer to Earth, and the moon used to spin at a faster rate. It had more rotational angular momentum, but over time the moon's rotation has slowed down, but its orbit has gotten bigger. So its orbit is getting bigger as time goes on, and it has slowed down. So at this point it's in what's considered a gravitational lock, where the same side of the moon faces the Earth all the time. So we're only able to see one side of the moon anymore. It used to be, I don't know how many millions or hundreds of millions of years ago, maybe billions, that we could have watched the moon rotate. You go out at night and you could watch the moon rotate from one to one side to the other. You could see new features of the moon come into view, but that's no longer the case. And that angular momentum of that higher spin is now in the orbital motion of the moon. So angular momentum can switch back and forth. Now here's the example on that front page. Here is an ice skater, and the ice skater is able to pick up some angular momentum, so they can go and skate and spin, really fast. What they can do is they can put their arms out and then pick up speed here, and then when they bring the arms in, they still have the same amount of angular momentum. Now what's happened here is that since there's no outside torques, when the skater brings their arms in, the only thing that's changed is the distribution of the mass. And so as a result, if you can get, here's the skater over here, let's say that there's a rotational inertia I naught, and they're spinning at a speed of omega naught. Well, if you can make the I naught smaller, that means that the omega will increase. And so that's what happens when, skater brings their arms in. They've reduced the rotational inertia, and since angular momentum is conserved, this product of I times omega remains constant, then they spin much faster. Same thing with the diver here. So with the diver, it's angular speed. With the diver, here's the diver jumping and then rotating. So they got a certain amount of angular momentum from the dive itself. And then when they do the tuck, the rotational inertia goes down and they can spin faster. So you can actually control the speed of the rotation that way. Here's an example. This is in every physics textbook. I guess this works. You've got an object on a table. There's a hole at the center. And so what you can do is you can create tension on that string. And since this is one of those frictionless tables, so the table is frictionless, and that means that this block just keeps spinning around on this table. They've given us some numbers here. They're saying that the mass is moving in that circular pattern with a speed of 2.4 meters per second with a radius of 0.80 meters. And again, the person's holding the string here, and since it's frictionless, this block just keeps moving forever. What happens as the string is pulled through the hole? So this is kind of like, it's kind of like something in orbit, I guess. There's a gravitational force here. What would happen, though, if we were able to take that object and vary the value of r? So in this case, if we vary the value of r here, then what happens? Is it going to go at a faster speed? Is it going to go at a slower speed? Is it going to continue to circle around at the same speed? And so here's the example. Here is the mass. Here is the velocity. Here is r for that circular motion. And so what we've got here is r is directed from the axis out to the center of the object that we're looking at. There is a tension force that is a force in newtons pulling the object back towards that object. Now, there's no torque. And the reason that there's no torque here is that when I look at the force and the lever arm are lined up with each other. They're in opposite directions. But when there's no perpendicular lever distance here. So if the lever distance is r, well, it's not, I would need a force in this direction to either speed the object up or a force here to slow it down. But the force we have here is not going to create a torque. Now, if there's no torque, then the angular momentum would have to be constant. So that says that we can say that currently the angular momentum is given by m v1r1, and if we shorten the value of r from r1 to r2, well, the v2 will change. So I can set the before and after angular momentum equal, and then solve for how fast this thing will be spinning. So since angular momentum is given by mvr, and since angular momentum in this example is conserved and it's constant, that says that when r becomes smaller, v is going to be higher. So when we shorten that distance r, v is going to go up. Now, we've factored out the m's and we just said v2 equals v1, r1 over r2. This was given as 2.4 meters per second. And then these were the distances. So the original distance was at 80 centimeters. That is getting shortened to 48 centimeters. And from that, we can solve for velocity 2. And velocity 2 is going to be faster, and this is what it works out to be. So that's the idea, is that if we pull that string in, it's going to travel faster in terms of a linear velocity. It has a shorter distance to go, and so the omega definitely is going to increase. It's going to complete the period of these circles is going to get less and less. Here's another example. I know this is, these are ones you kind of have to slow down and stop and think about and look at, because circular motion is just more difficult to think about than linear motion is. But angular momentum is kind of guiding us through this. Here is a clutch assembly. So what we've got here is a mechanical system. This one is being driven by some kind of an engine or a motor. And then this one currently is at rest. But what we're going to do is we're going to allow this, push this down so that it comes in contact with the rotating platform. Now, what numbers have they given us here? The two plates each have a mass of 6 kilo. Oh, no, it's 6 and 9 kilograms. Sorry, but they have the same radius. That's 0.60 meters. That's 60 centimeters, and that is a radius. It's not a diameter. Plate M is brought up from rest to an angular velocity of omega 1 is equal to 7.2 radians per second. And that all happens in 2 seconds. So the first thing we're going to do is we are going to exert a torque on the lower plate. So that lower plate is going to have a torque acting on it, and that's going to bring it up from rest up to some rotational speed omega. Now, what they want us to do is calculate how much angular momentum is there and what was the torque required to bring the lower plate up to this speed, 7.2 radians per second, in just 2 seconds. So we got to bring it up to speed. And then finally in part C, I hope it's finally, next, plate M, initially at rest, free to rotate, is placed in contact. So there's going to be like frictional forces. So what's going to happen here is this is brought down in contact with this, and I'm guessing frictional forces or other forces, it's going to eventually be spinning at the same speed. Now, what they're saying here is this was driven initially and brought up to speed, but then it was isolated. Because what they're saying is when the other plate comes down and makes contact, it's like an inelastic collision. If you want to think back to chapter 9, what's happening here is plate, the upper plate comes down, runs into the lower plate, and it's like an inelastic collision. And what we can do is say the angular momentum before equals the angular momentum after. And so for that to be true, the plates would have to be isolated from whatever brought them up to speed in the first place. So let's take a look and see what we've got. So first of all, in part A and B, here is the plate. Let's exert a torque. Now the direction for torques, when we think of it as a vector, is along the axis of rotation. So that's kind of interesting to think about. And then the acceleration we get is going to be the torque divided by the rotational inertia. Now, we talked a little bit about in chapter 10 that there are what we consider to be symmetric axes of rotation, and this is an example of a symmetric axis of rotation. So this is a cylinder, and we're rotating it around one of its principal axes. That means that it's a balanced system, and it's balanced and it's rotating around its center of mass. And that says that the torque will be in the same direction as the rotational axis. That's not in general going to be true. As we talked before, the rotational inertias can be complicated if we're rotating them around axes that don't have a symmetry to them. So the rotational acceleration we have here depends on the torque divided by the rotational inertia. I'm going to go ahead and just say the rotational inertia it's the rotational inertia for a cylinder. So these are two cylinders that are being brought into contact with each other. The mass of cylinder 1 was given as 6 kilograms, 60 centimeter radius, and so the rotational inertia is 1.08 kilograms meters squared. And then the other kinematic information they gave us was that it starts at rest, and then it spins up to a speed of 7.2 radians per second, and that takes place constant, a constant angular acceleration, and it takes place in 2 seconds. And so what we've got here then is the acceleration, the angular acceleration, is 3.60 radians per second squared. All right, now let's take a look at how much torque would then be required. So using the second law of motion, the torque that we're looking for is the torque that can accelerate this at 3.60 radians per second squared, and the object itself has that much inertia. So if I want to get that much inertia, bring it up to speed, up to a rotational speed of 3.60, the torque I'm going to need is 3.89 newtons times meters. Okay, so I hope that shouldn't be too different from what we saw in chapter 10. Now what we're going to do is we're going to find out how much angular momentum is built up in that rotating system, and for this we can use I omega. So again, the I omega stuff is kind of new, but think, oh, it's like linear momentum. You know, linear momentum was mv. mv, 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 yeah, I can calculate linear momentum. Well, angular momentum, it's I omega, I omega, I omega for these objects. So I can take the rotational inertia, multiply by the omega value, and it says that this is how much angular momentum has been transferred into this object when we bring it up to speed. So, and again, what we're saying is that the torque was responsible for that. For a constant torque, we could take the angular momentum, divide by time, and that should give us the torque. I think that works. So if I take the 7.78 units of angular momentum and divide through by 2 seconds, what we are going to have is 3.89. Now this has units. Should have written these more similarly, I guess. This is newtons times meters times seconds. So newtons, meters, seconds, and then dividing by seconds puts us back into newtons times meters. So that's kind of how everything, all of the different quantities fit together. Okay, so here we are in part C, and before what we're going to say is there's just one of these cylinders, and it's got this rotational inertia, and it's got this angular velocity. But after the two cylinders come into contact with each other, then I've got to take into account I1 plus I2 times omega 2. So now they're both going to be spinning at a rotational velocity of omega 2, but the rotational inertias I'm going to have to add together. So again, it's basically an inelastic collision that has taken place. So if I carry through the algebra, if I take this expression for angular momentum and the after expression and set them equal and solve, that's telling me that the rotational velocity after the collision has taken place, after the two cylinders have come into contact, so they're both spinning at the same rate, is given by I1 over I1 plus I2 times omega 1. Now these are a couple of cylinders, and so the rotational inertias are given by 1/2 mr squared, and so I got a 1/2 mr squared here and a couple of them in the denominator. All the 1/2s and r squareds cancel out because they were all the same. So that's gone, and I'm left with m1 over m1 plus m2. Again, it looks like an inelastic collision. And then I put in the 6 kilogram and the 9 kilogram numbers, and it says that the speed afterwards is only going to be 40% of what the rotational velocity was before. So if the initial speed was 7.20, after the two have collided, after the two cylinders have come into contact and they're spinning at the same speed, that's going to be reduced to 2.88 radians per second. Ooh, all right. So again, I know I moved to these examples really fast. I have to pause because it's like, I got to stop and think about that. What just happened? All right, so angular momentum before we set it equal to angular momentum after. What we're doing is getting an algebraic expression for the angular momentum before, an algebraic expression for the angular momentum after, and then setting those two equal to each other. All right, here's a neutron star. Stars that are fairly high mass, relatively high mass stars, once they've run out of fuel in the nucleus for nuclear fusion, then they're kind of left with the outward force from the nuclear fusion drops off. So when the fuel in the core is used up, there's no outward pressure supporting the star. And as a result, the gravitational forces take over. You know, gravity's been very patient during all the time when the star was shining, but now that there's no pressure pushing outwards on that star, gravity kind of takes over and it collapses the star. So our best understanding of how neutron stars form suggests that the size of a neutron star, if we had a star the size of the Sun at 700,000 kilometers of a radius, but with twice as much mass, and it's rotating one rotation every 100 days. Now, the Sun rotates what? It's like once every 20 or 25 days, and the Sun doesn't have, it's not a rigid structure. So not all regions of the Sun rotate at the same rate. There's a difference between rotation along the equator material, for example, versus the poles on the Sun. In any case, this is kind of similar to the rotation rate of the Sun. This is actually slower. There's only one rotation every 100 days. That's a pretty long period. What would happen if we had a gravitational collapse, and now the neutron star, which includes all the mass of the original star, but it has collapsed down to a size of just 10 kilometers. So this is an extreme example for angular momentum conservation. So the star retains all of its mass, but a star that was hundreds of thousands of kilometers in size is now tiny. It's like 10 kilometers across. And so, here's this enormous star, and it's rotating at this pretty slow rate, omega 1, but it's going to collapse down to this really tiny object. How fast is it going to be rotating given that angular momentum is conserved? So the angular momentum in this neutron star matches the angular momentum here. Well, here we had all this mass spread out over hundreds of thousands of kilometers. The mass now is just over a tiny region. That neutron star is going to be spinning at a really high speed. Now, just a quick aside here, what is a neutron star anyway? Well, it turns out that when we look at a star made out of hydrogen and helium, and it's the electrons that kind of big and bulky. Electrons need their space. So electrons kind of take up the space of a star, and when the gravity collapses the star, it collapses it down to a point where the electrons are packed about as close as they're comfortable being packed, and then the star stops collapsing. But for higher mass stars, you can actually set off this particle reaction where the electrons become neutrinos. Now, neutrinos are neutral. They're not attracted electromagnetically to the other particles, and so the neutrinos just fly off. So this is a way to get rid of the big, bulky electrons. Now, at the same time, electrons turning into neutrinos does not conserve charge. At the same time, that reaction is coupled with protons turning into neutrons. This is what we call a Feynman diagram. We'll see these kind of at the end of Physics 4C. And so this is a reaction that happens through what we call the weak force in nature. But what we've done now is the electrons needed a lot of space. Neutrons don't need nearly as much space. If you're familiar with atoms, for example, how big is the nucleus? How much space do the protons and neutrons take up? And it's tiny, right? protons and neutrons are little tiny objects compared with the big bulky area where the electrons fill. And so now the star collapses much more. And so that's what it explains, or this is the reaction going on in the formation of a neutron star. So these neutron stars can be really small. And we actually have calculational methods. Again, we'll see this in Physics 4C, last chapter on astrophysics. We can actually go in and estimate the size of these neutron stars that are predominantly made out of neutrons. The protons have been converted into neutrons, and the electrons have been converted into neutrinos. So anyway, for Physics 4A, what we need are the starting radius, final radius, okay, 700,000 kilometers down to 10, and then the initial period. And what we want to do is this. Let's see, here is angular momentum before, angular momentum after, and we just set the I omegas equal. Now, the rotational inertia for a sphere is given as 2/5 mr squared, so that's what we'll write in there. And then for omega, they weren't really asking about speeds of rotation, they were asking about period of rotation. So for omega, we can substitute in 2 pi over T1 and then 2 pi over T2. Now something I should point out here, I guess, we are assuming that these spherical objects like the sun and the star and the earth, the rotational inertia is given by 2/5 mr squared. That's not really accurate entirely because they're not uniform density. So Earth is much denser at its core than it is on the surface. The surface, rocky material is not nearly as dense as the core. Same thing for stars. The core is much denser. So the rotational inertias aren't as large. This is an overestimate as to how large they are. But still, it's kind of an interesting example. So let's go forward with that. So I can put in the formulas for the rotational inertias of the original star and then the neutron star that it forms from. And again, assuming that the mass remains the same, well, the m before matches the m after. And you can see how much stuff factors out here. So the only things that are going to be left are the diameters, or the radiuses, before and after, and the periods. And so this becomes a ratio. What we can do is bring the T2 over to here. We can take the R1 squared and bring it over here. So it says that T2 over T1, the periods, are going to be proportional to R squared, R2 over R1 squared. And so when we look at this, the period is going to decrease by a factor of 2 times 10 to the minus 10. It's going to, the period is going to decrease by 20 billion times. So what we can do then is, we can put the numbers in and just calculate. So I got this ratio here, and if we do the conversions from that, it turns out that the period of rotation now is about 2 milliseconds. So this thing is going to, and I took the period and inverted it to get a frequency of rotation. It says this neutron star is spinning 567,000, not thousand, sorry, I almost exaggerated, 567 times per second. I don't know where that 1,000 came from. So this is impressive enough, right? 567 rotations per second on this neutron star. And yeah, we have evidence that these things really exist. We have stars. As the neutron stars rotate, neutron stars are radiating energy across different parts of the light spectrum. And the energy tends to come out through the polar regions. So if we've got a rapidly spinning neutron star oriented so that the polar regions go past us, this is kind of a lighthouse model. So it's kind of like if you think of a lighthouse with light coming out two sides. As the lamp in the lighthouse spins around, that light comes into view and then it disappears. So we see stars with this very regular period of luminosity, and that's not unusual to see something like that, these flashes of light are happening hundreds of times a second. So, and we feel pretty confident those are neutron stars that we've identified. All right, here's another angular momentum example. So what we've got is we've got a really big circular platform, and we're going to rotate it around one of those symmetry axes through the center of mass. And what they're telling us in this example right here is that for a symmetrical object rotating around an axis of symmetry, the angular momentum direction is the same direction as the angular velocity. So if I've, oh, did I get this backwards? Oh no, I think I got it right. So the person here is going to start running around in what we would call the positive direction. And what we can do is say that if we use a right-hand rule for that. So here's one of those handed rules. So a right-hand rule would say that if I bring out my fingers and follow the direction that that person is rotating around that axis, my thumb will point in the direction of the angular velocity and the angular momentum. So this person's angular momentum is officially designated as this direction, and then the left hand is keeping track of negative values. So if I put my fingers in the direction, I guess it's not really left-handed. So if I put my fingers in the direction here, where it's left-handed, then the angular momentum is going to be in the opposite direction. So, so these two angular momenta are in different directions. Now, I think what they said here, or maybe they didn't say it, is imagine the platform starting out at rest. So if the platform's at rest and the person's at rest, then there's no angular momentum. But when the person begins to walk on this freely rotating platform, they begin to pick up angular momentum in this direction. So it's represented downwards. And then the platform begins to pick up angular, oh, we got it backwards. The person begins to pick up angular momentum in the positive direction, and the platform begins to pick up angular momentum in the negative direction. So, so the left-handed motion actually gets, the arrow ends up being downwards in the picture. So if the person runs faster and faster, then the platform goes faster and faster in the other direction. And if you go in and you calculate the amount of angular momentum in the person and the amount of angular momentum in the platform, they still add up to 0. If there's been no friction in the platform supports. So if this circular platform that's freely rotating is on a fractionless supporting system, then the angular momentum will be conserved within that system. And here it is, running on a circular platform. Be careful about running on circular platforms. So it's a 60 kilogram person. They're standing at the edge. It's a 6 meter diameter, which means 3 meter radius. And it's on frictionless bearings. It has a moment of inertia of 1,800 kilograms meters squared. The platform is at rest initially when the person begins running at a speed. So they start running, and at some point, they are moving at 4.2 meters per second with respect to the Earth. So we need an inertial frame to make these measurements from. The platform is now rotating in the opposite direction. So it's not like a delay here. As the person picks up speed in one direction, the platform is going to pick up speed in the opposite direction. And at each instant, we can calculate the angular velocity of the platform by setting the angular momentum equal. So here's the angular momentum in the person and the angular momentum in the platform. They're going to have to be equal and opposite, equal amounts, but in opposite directions. And so I thought the easiest way to do it is just use absolute magnitude or absolute value on these. And then I'm going to represent the person as MVR, because the person's mass is all kind of concentrated at that one location, right? So MVR seems convenient to represent the angular momentum of the person. And I omega seems to be convenient to represent the angular momentum of the platform. So that's the idea. I can use whichever formulas are going to be most convenient. So with the angular momentum, using this formula, I can, by setting the angular momentum equal, I can solve for the angular velocity. That's what they wanted. By taking mvr over I put in the mass of the person. Boy, I hope I did. I divided by 2. That's the radius. Person's going that fast. This is what they told us the rotational inertia is. And so we're, the platform's going to be rotating at 0.42 radians per second. Now when we set up the formulas like this, that the omegas naturally come out in radians per second, but that's not always the most intuitive way to think about it. So I went in, took that number, and I said one revolution, or one rotation, is 2 pi radians. And so what that became was a frequency. How many times per second is this thing rotating? And it's completing 0.0668 revolutions per second. Now that's kind of hard to think about too, and so I did the inverse. So the inverse of this number, 1 over 0.0668, gave me 15 seconds. So this platform, when the person's going at that speed, the platform is going to have a period of 15 seconds. It's going to be rotating every 15 seconds. Now, here's the platform, rotational inertia, and they told us that. They just gave us the value of I at 1,800 kilograms meters squared. So I thought, let's just guess it's a cylinder. And so I used the 1/2 mr squared rotational inertia formula, and I went in and solved for m. They didn't ask us to do it. I was just curious how much mass the platform is, and it worked out to be 400 kilograms. So running on a platform. All right, let's think about these. These platforms are kind of handy. So here's another one of those platforms. It's frictionless, so that platform rotates freely, and it's supported right at the center, so that we're looking at rotations around this symmetry axis. What we've got here is that this person is holding on to, this is your physics teacher, and the physics teacher is holding on to a bicycle, and it's rotating, and I can use that right-hand rule and say that if it's rotating like this, then the angular momentum is in that direction. Now, we don't know how this happened, so I'm a little confused here. So I'm thinking what happened is the physics teacher probably got that bicycle wheel going when they were standing off the platform, and then they stepped onto the platform. Now, what they're going to have the physics teacher do now is flip the bicycle wheel over. What's going to happen? So what happens when you take a spinning object that has a bunch of angular momentum built up and flip it over? Now you might think, well, it's just going to spin at the same rate. Doesn't that mean it's got the same angular momentum? And it doesn't, because angular momentum is a vector. So if the person takes this bicycle wheel that's like this and flips it over like this, well, now it's spinning back the other direction. What used to be angular momentum here is now angular momentum in the opposite direction. That's a significant difference. Okay, so if we were back in chapter 9 thinking of linear momentum, what that would correspond to is I have an object that comes in at some speed with a certain momentum, it bumps into something, and then it turns around and it goes back in exactly the opposite direction. And what we found is, when you saw a reversal of linear momentum, that was a very large momentum transfer. So the object comes in with all this momentum, it's brought to zero, it's brought to rest, and then it's pushed back out with opposite momentum. Well, let's see how this might work. So here's what it looks like before. We've got the bicycle wheel, it's spinning, and I put some numbers in. I thought that might be useful to. So let's say that it has 5 units, newtons meters per second, not per second, but time seconds, sorry. Newtons times meters times seconds. It's got 5 of those units, and that's how much angular momentum is built up in the bicycle wheel before. Now, when the person flips this over, the angular momentum now is going to be in the opposite direction. So if initially it was +5, well, the angular momentum in the bicycle wheel is now -5 units. So what would happen is this. Initially, all of the angular momentum is in the bicycle wheel. After the person flips the bicycle wheel over, that angular momentum is going to be in one of two places. It's going to remain in the bicycle wheel. It's now spinning at the opposite direction. But it's also going to be a possibility of transferring to the platform. So the platform is free to rotate around the axis of rotation that we're looking at. And so what will happen is if I take L1 plus L2 combined, the total angular momentum after needs to match the total angular momentum we started with. So that says that the platform will then begin to rotate. And the platform is going to end up rotating in the direction that the bicycle wheel was rotating before. Right? We started off with 5 units. We need 5 units here. But wait a minute, this is -5. What value of L2 could I come up with when added to -5 would give us 5, and that number would be 10. So the before picture, we have 5 units in a direction that we're calling positive, and that means combined here we have to have 5. Well, if this becomes -5, then the platform is going to rotate with 10 Newton meter seconds of angular momentum. What happens now if the physics teacher turns the bicycle wheel back how it was? Right, and so the platform stops rotating. So we can go from before to after, and then we can go back. Well, we can't go back to before. It's an after, but we can go back to this picture. So we can go from here and then flip the wheel over and the platform starts moving. If we now take this and flip it back over again, we're back to that picture. Okay. And this is all assuming that we've completely isolated these objects. And what that means is this platform needs to be up on some frictionless bearings. Now, you might say, well, what if the platform's not there? Where does the angular momentum end up? And it ends up in the whole planet. So if we turn that wheel over, then if the person's standing on the planet and there's friction, then it gets transferred into the entire planet. And the planet's so big that we don't really see much difference in the Earth's motion. When we take a bicycle wheel and move it back and forth, and you go, did you feel that? Did you feel the Earth move when we do this? Probably not. So the platforms are great because what they allow us to do is isolate things. Now, what I always think of when I see these rotating platforms is I think of watching astronauts in space, in orbit, repairing satellites, right? So they're out in the space shuttle, and they come out of the space shuttle, and you've got this satellite, and it's rotating. And, I mean, you know, part of the astronauts' training has got to be a reminder of just how much rotational inertia those satellites have, and not to grab onto anything, because they've really got to carefully plan out how are they going to bring that satellite's rotation down to rest, and then do the repairs, and then bring the satellite back up so that it's spinning properly to help maintain its orientation. All right, we are ready to talk about a new vector operation. This is referred to as the vector product or the vector cross product. Now, cross doesn't mean angry or upset here. Cross product means, it means we use this symbol. Now, you guys remember the dot product, right? So the dot product took different components of two different vectors, multiplied them together, following a certain formula, and it gave us a scalar. Cross products are a little different. They're called vector products because when I take two vectors and operate on them with this cross product definition, I end up with another vector. Now, the vectors that we've been looking at, all these rotational vectors can be expressed in terms of cross products of different quantities. But the one rotational quantity I think it's most clear in introducing this is torque. So torque, up until now, we've been saying is a lever distance times a force, but now we're going to generalize that. What happens if here is an axis of rotation, and we're going to move on from an axis of rotation to a point of rotation, a point around which the object is rotating. And what we do is we start by measuring a lever vector from the axis of rotation, or the point of rotation, out to where a force is being applied. And notice now, the force is not perpendicular. Now in chapter 10, what we did was we took that force, divided it up into components, and we said only the component that's perpendicular is going to contribute to being a torque. Let's take a look and see what that would mean for us. So here's a picture, and here is an axis of rotation, or a point of rotation, the origin. And then we'll say that here is a lever vector, and the lever vector is going to have components to it, x, y, z, in general. So a lever could have, in this example, it's just two dimensions, x and y, but there is an x component to the lever, and there's a y component. Now the force is tipped at some other angle, and it too has components. Well, the torque, from this picture right here, if you were asked, back in chapter 10, how much torque is going on, you could match these things up, right? You could say, well, there is a force in the y direction, there's a force component, and if I follow that force back, it has a lever distance of x. So there is a torque that is the x component of the lever vector, the r vector, times the y component of the force. But that's not the whole story, because there's also a component of force in the x direction, and when I trace that back, its lever distance is y. So this is lever distance times force component, lever distance times force component, and that's in the opposite direction. So I have to have a minus sign between it. So that's kind of interesting, that the way we have torques, the way we've defined torques, if we take the individual components of the force and the individual components of a lever vector, we've been able to identify which components go with which components in determining how much torque. It's got to be perpendicular. And so x is perpendicular to fy, and y is perpendicular to fx. So if we generalize this statement into three directions, that's what it looks like. So those three equations, calculating the torque in the x direction, in the y, and the z, would follow this pattern of components. Now, the way you do this is, once we've established that the torque around the z-axis, this would be around the z, because what's going to happen as a result of this torque, the thing's going to start rotating. And the rotations are taking place in the xy plane, and that means the axis of rotation is the z-axis. So we'll set up our coordinate system so that the z-axis is right at the center, and z is coming out of the board. So that would say that the torque is the z component. So the z component of torque is given by this expression, the same one here. And then what we can do is we can say, okay, if this is zxy, then I can loop through xyz. All I have to do is just write the indices in the same order. This is x, y, z, y, z, x, z, x, y, and then I subtract off the product with the subscript reversed. Now you can draw pictures and show that this really is how it works. So mathematically, we're just arguing that that's how we can keep track of the indices. Now all of this information gets packed into that equation. So that's what's called a vector product or a vector cross product. And as you can see, it's more complicated than the scalar product. The scalar product was, or the dot product, that was not so difficult. This one you have to really stop and pay closer attention. Now it turns out we can show, using some fancy algebra, that the magnitude of the torque, of a cross product in general, is the magnitude of vector number 1 times the magnitude of vector number 2 times the sine of the angle between them. Now with the dot product, that was a cosine, right? But this is going to be a sine, and we will we'll take a look at how this works. So here's another general statement of the vector cross product, and again we said that this works for torque. Torque is one of the most obvious examples of using a vector cross product. So in general, the magnitude of the cross product, the magnitude of A cross B, is the magnitude of A times the magnitude of B times the sine of the angle between them. Now we've got to take a quick look. What's the angle between these vectors? Because R is here and F is here. Is the angle here? And it's not. The way to find out the angle is to take the R, and I should have done this here, take the R and bring it over and set up a vector diagram, and then bring the F over, and so R cross F has an angle between those two vectors when you take the vectors and bring them off to the side as a separate vector diagram. Okay, so here's another general statement as to what that formula looks like, and so you can see how they're keeping track of all the components that are there. So this is saying that, now they say that this can be done using a determinant form, and that's fine. So, you know, in the x direction, we'll use the I unit vector, and that would be AYBZ minus AZBY. So it does turn out that the rules for taking the determinant of a matrix, but I guess I just prefer just writing the whole thing out. I mean, that's my preference, but the determinant approach can also be used for these cross products. So here's some interesting properties of cross products. If I take a vector and cross it with itself, it's 0, because the angle between the vector is 0. And so the sine of 0 is equal to 0. So if I have two vectors that are lined right up, their cross product is 0. What I really need to have a large cross product is to have two vectors that are perpendicular to each other. So torque comes to mind. If you want a lot of torque, you want the lever vector and the force vector to be perpendicular. Another interesting property for cross products is if you reverse the order, it changes the sign. So you can go through and look at those definitions we've written on those previous slides and demonstrate each of these properties. It's kind of interesting. There's a distributive property for taking cross products, and then there's also the product rule for taking derivatives. That also works. So we're not going to use, so, well, let's see. I'm going to say these are the ones that come up the most. If I see a vector, if I see two vectors pointing in the same direction, the cross product is 0. If we take a cross product and we reverse the order, then we have to remember that there's a minus sign that needs to. So the definitions of cross products have to be written. So when we write torque is R cross F, torque is not F cross R. It's got to be R cross F. The way that we've defined this, we need the lever vector to come first. And so here, here again, it's a diagram. So we pick a point around which we want to measure torque. So notice we're working around not necessarily an axis, but rather a point. And then once we can see the torques, that will give us information about what axis of rotation we might end up observing taking place once we've done that. So that's the picture. Here's the origin. Here is some kind of a lever vector out to where a force is acting. And again, what I have to do is take the R, move it out so that it's out here where the force is. And then when I look at those two vectors, then I can take the angle between them. Again, I guess I should have written that onto the slide. Okay, I think we are probably, that's probably enough for today. So I'm going to stop there. You guys have questions? So I hope to see you guys in office hours with whatever questions you've got.